And it's my great pleasure to introduce James Pascoe from the University of Florida, who will speak on the tracial fundamental group.
So thanks. So I would, so first of all, I'd like to say thanks for organizing this. I think adapting it to a semester-long program has been very good for the field. So I'm glad to be back at Fields. I wish I could be in Toronto, but you know, these things happen. I would like to advertise that we will have SEAM 38 March 5th through 7th in 2022 at UF. Our current plan is for it to be in person. So it should be an exciting event. I'd love if you'd all come down here. Especially, I've heard a rumor that it's much colder in March other places than it is here. So I would highly recommend checking it out. If you Google SEAM 38 UF, you should find it, or if you, a good place to find out about this kind of stuff, general events, and you should submit, if you're hosting events, Ryan Tully Doyle has a new website, or well, a website that's being developed called operatortheory.org, which is supposed to be some sort of like just a nice website that's being developed. I would check it out if you've got suggestions for him. That would be great. It's sort of his baby, and it's been pretty, it's an exciting project to sort of centralize a lot of resources that we have for our operator theory community. So today what I'm going to talk about is something sort of, so I want to talk about basically analytic continuation, but I want to talk about it in terms of how analytic continuation interacts with the functional calculus. And the point is that if we want to sort of understand the analytic continuation of functions evaluated on matrices, we might actually get better results than we get if we're just trying to do analytic continuation in the classical case. So let's start out with that. So to start out, we're going to talk about analytic continuation in C. In the complex plane. And then we're going to talk about how that motivates topology. So let's start out with a fairly simple setup. So we've got B inside of E, inside of C. So we have a subset B, which we're going to have this one be open. B is going to be open and simply connected. E is going to be an open connected set. And C is the complex plane. Okay, and so and if we have a function f, taking our little set B into C, which is analytic, then, so we've got our big set E, it might have a hole in it, something like that. And then we've got our tiny set B. And if we have our function f defined on B, well, because B is simply connected, we've got the Monodrome theorem on B, which is nice. So then we can talk about analytically continuing a function from B to all of E or along any path in E by, well, what do you do whenever you want to analytically continue a function? First, you expand a power series, you expand, then you take a point here and you expand a power series, and so on. So we can sort of, really we need to have double overlaps here, I guess, but you can sort of analytically continue along a path, and you might keep doing this for a while. And then you might get back to where you started, but you don't necessarily know that you have the same function that you had whenever you started. Like, for example, analytically continuing the log, we might differ by a constant or something like that. Of particular interest for reasons like related to, say, the Monodrome theorem are functions which analytically continue along every path inside of E. So functions on B which analytically continue along every path in E. So we say F, taking B into C, is a global germ. If F analytically continues along every path in E. Okay. So global germs, those are sort of like, so those are functions which so the monodrome theorem, what does that say? It says if E is simply connected, then, and well, I guess, and F is a global germ, then F continues to all of E and has a single valued analytic continuation there. So this is sort of a starting point for topology, in terms of mathematics. I think one of the big reasons why we needed to develop topology was to understand, say, contour integrals and understand homotopy and analytic continuation. And so this monodrome theorem sort of gets at the simply connected hypothesis, sort of telling us something about how analytic continuation works. So an observation here is that if I have two paths, so if I have gamma 1 and gamma 2 are paths in E with same endpoints, then gamma 1 is homotopic to gamma 2 if and only if every analytic continuation of the global germ along gamma 1 agrees with the same thing along gamma 2. So if I analytically continue along one path, I can deform it to this other path if and only if actually those agreed for every analytic continuation. This is sort of related to the uniformization theorem. But maybe that's not so important for today's talk. So the point is that one way you can think about this is that if I had, the point is that these are homotopic if and only if there isn't a hole in the domain. And if there is a hole in the domain, then we can have a function that, say, like log, which has a hole, which sort of creates a branch cut around this sort of removed part of the domain. Okay. So now to review our, so we have this way of concatenating paths. So if I have one path going from A to B and another path going from B to C, then I can, let's use a different color here. So then I can write down this whole thing, this whole path that is the join of these two things is a way to concatenate these paths. And we're going to write that down as gamma 2 times gamma 1. We could have written it in either order, but chosen to write it that way. Okay, so the next thing that I want to do is talk a little bit about the fundamental group. of this domain E. So that's going to be the set. So pi1 sub E is the set of paths from some fixed x in B to itself. So the point is that because we've assumed that E is connected statically in this talk, it doesn't matter which point we choose, but we have the set of points from x to it, the set of paths from a fixed point x to itself up to homotopy. So what I should say here is we should note that this pi1 sub E acts on global germs via analytic continuation. So the point is that if I have, here's B, if I have a global germ defined upon B, and then I analytically continue along some path, call it gamma, I start out with a function defined on B, then I analytically continue it along in this cartoony way, and then I might get a different function on B. So the point is that this group acts on this global germ. I take the global germ that I had here to start, then I analytically continue it along this path, and then I get a new global germ out. And the other thing to note here is that the action of pi1 sub E is faithful. So what does that mean? Well, what that's supposed to mean is that, i.e., if we have a gamma inside of, given gamma inside of pi1e, inside the fundamental group, we have that gamma dot f equals to f for every global germ if and only if gamma is the trivial path. So just sort of the path from x to itself up to homotopy equivalence. Okay, so this is sort of the classical setup for analytic continuation that I wanted to review. Now let's talk a little bit about the functional calculus. Okay, so if I have a function taking my set, taking a set E into C, which is analytic, and if I let A be, say, a matrix, we could really do this with operators, but I'm going to do this with matrices today for whatever reason, with spectrum in E. Then what I want to do is I want to figure out how are we supposed to define evaluating this function f at x. So let's sort of review that. So how do I evaluate f of a? Well, first I need to choose a contour gamma in E, which winds exactly once around the spectrum of A. And then I define the evaluation of f in the functional calculus. Come in. Oh, sorry, 1 second. Okay, yeah. So functional calculus at A is supposed to be 1 over 2 pi I times the integral along gamma of f of z over z minus a dz. So this is our way of defining the evaluation of f at A in the functional calculus. Okay, so we just use the Cauchy integral formula to do that. So if A is diagonalizable and A is equal to, say, S inverse, a diagonal matrix with some eigenvalues on it, S, then, you know, f of A is supposed to be equal to S inverse, and then I take f of the eigenvalues. And so really, this is a natural way to evaluate this classical functional, this classical functional calculus agrees with this on diagonalizable matrices. Okay. So now I also want to talk about a slightly different, so the reason why I decorated f with this little f to say that I was evaluating in the functional calculus, the classical functional calculus, is that I also want to talk about a related functional calculus, and we'll see why in a minute. Okay, so the tracial functional calculus, if I want to evaluate f in the tracial sense, at a matrix A, I'm just going to have that be equal to 1 over n times the sum of f of the eigenvalues. So these lambda i's are the eigenvalues. I equals 1 up to n. So, okay, and so what we're going to try to understand is how do these functions, this f evaluated in the functional calculus and this f evaluated in this tracial functional calculus, analytically continue, and what's the theory of analytic continuation of those kinds of things. And what I'm going to say about those also could apply to several non-commuting variables, but I'm essentially taking the one variable route for today. So, okay, so let's sort of see. So now we've got our functions that we want to understand. So now we need a version of the fundamental group. So that's going to be our next step. So we have something which we're going to call essential paths. So if I let x and y be inside of our set, the set E that we care about, and which is then a subset of C, we say a path gamma, which maps into n by n matrices over C, such that the spectrum of gamma sub t is contained inside of or inside of E. So we have a path such that for every time the spectrum of this path is contained inside E, we say that this essentially takes x to y if, it essentially takes x to y if gamma of 0 is a diagonal matrix with a bunch of x's on the diagonal, and gamma sub 1 is a diagonal matrix with a bunch of y's on the diagonal. So it's sort of like taking it's like a path between X times the identity and Y times the identity, but we're allowed to move through matrices, which is going to give us a little bit of extra flexibility compared to what we have in the classical case. So something to note here is that we can continue this f evaluated in the functional calculus and f trace along such paths. Yeah, so that's sort of the point, is that these essential paths are the kind of paths we might want to analytically continue along generally. And then I need a way to define concatenation, which is going to seem kind of funny to start, is if I've got two paths, I'm going to take gamma 1 or gamma 2 times gamma 1. That's going to be equal to just the same thing as concatenating. Well, so the point is that this might map, if you say like gamma 1 maps into Mn, and gamma 2 maps into MM, then we might have a problem with respect to the sizes. So the point is that how do we fix that? Well, we just concatenate two paths where we fix the sizes by direct summing those paths with themselves, which seems a little funny, but okay, that's what we're going to have to do for now, and we'll rectify that momentarily. But this is the right way to concatenate. So the short answer. So the full fundamental group so we're going to call that pi full sub E. So now I'm going to define what I mean by the full fundamental group. So this is going to be, so pi full sub E is going to be the set of paths from X to X from some point. Yeah, so we fix X and B. Or well, an E really, but doesn't really matter. But yeah, so if we're still on the setup of having B simply connected inside of E, inside of C, it's going to be the set of paths from X to X such that up to the following equivalences. So the first one, if two paths are homotopically equivalent, or homotopy, so first up to homotopy. And then the second thing is that I want, if I have a path direct sum with itself m times, I want to treat that as being the same as the original path. So if I direct sum the path with itself, so like I want to say basically things like, if I have gamma gamma, if I have a path and then I create a block diagonal matrix like this out of those two paths, I want to say that that's sort of equivalent to gamma, but I also want to allow myself to do that arbitrary numbers of times. Okay. So now this full fundamental group is an interesting object on its own. Before we even think about analytic continuation, let's prove a couple of things about it. We're going to prove things about basically, so the really remarkable thing is that this turns out to be an abelian group. So let's see how we see that. So the first thing that I want to note is that if I have gamma gamma, so if I have a path that's a path direct sum with itself twice, that's the same as taking, well, so that's the same as, I guess, taking the trivial path in the first slot and then taking the path in the second slot and then taking the actual path we wanted to take in the first slot and then the trivial path in the second slot. So here tree is the trivial path. So it's the identity element in this fundamental group. Okay, so what's even sort of maybe even more exciting is that if I have gamma tau, if I have gamma tau, that's actually equivalent to the path. So in this group, this is the same as the path tau gamma. So let's see why that's true. Well, if I take R of theta to be your standard rotation matrix, then, and I define this a map, gamma homotopy map, one path to another, is just given by, well, I take R of theta, I multiply by gamma sub t, gamma tau sub t. And then I take R of theta star. Then the point is that this homotopes one path to the other, because if I take theta to be, I guess, pi over 2, I get a diagonal matrix, or well, an anti-diagonal matrix, which then is going to swap the two entries. So this allows me to homotope one to the other. So now the final sort of thing here, so combining these two pieces of if I take gamma 1 times gamma 2, that's the same as taking gamma 1 direct sum with itself times gamma 2 direct sum with itself. So then that's supposed to be equal to, well, gamma 1 times tau gamma 1. And the same thing with gamma 2. So then what happens here is now I could rewrite this. So I could rewrite this as being gamma 1 squared, because this part is the same as, this is the same as, well, let's just rewrite this. I'll write it gamma 1 tau, because of this relation, I can swap the two. For the other one, I could swap the gamma 2 down. And so then what's the key here? Well, if we sort of do this now, this part commutes with this part. So what's the point there? So this is like gamma 1 squared tau times tau gamma 2 squared, okay, which then is equal to the same thing, but where gamma 2 is in the first slot. And so then if we sort of go back through this, then we end up getting that this is the same as gamma 2, gamma 1. Okay, so that's all fabulous or whatever, but let's see. So this gives us a theorem, is that this pi full of E is an abelian divisible group. And divisible just means you can take nth roots inside of the group, essentially. And an open question here, especially in the multivariable case, is this pi full torsion free? And we're going to see sort of a way to rectify this not being torsion free if we sort of restrict this fundamental group to basically cases where, so basically we want to restrict this fundamental group to be a fundamental group that's actually adapted to work with either the functional calculus or the tracial functional calculus, which is going to be our next little unit. Okay, so now let's let B again be open and simply connected, just so we remember what that is. E again open and connected. So we say F taking B into C is a global functional germ if f evaluated in the functional calculus continues along every path gamma in this pi fully. Okay, and so this is a global functional germ. We could also define the same thing, but for tracial germs, which I'll put in. Let's not use that bright of a pink. Let's use some sort of a more muted pink or purple, I guess. So we could also define this for tracial, and then we would just have to say that this f evaluated in the tracial functional calculus should analytically continue along arbitrary paths. Okay. So the note here is that this pi full E acts on these global germs. So global functional germs or global tracial germs. Okay, so, but the point is that it might not be able to distinguish between two different, like the point is that global germs might not be able to distinguish between certain paths in E. So we need to mod out by something to give us a function, to give us a fundamental group that actually works for our specific instances. And then we're going to get some nice theorems out of that, which actually are going to explain a lot of things that have happened in non-commutative function theory in a minute. So if I'm going to define pi functional of E just to be this pi full, so be modded out by the set of gamma such that gamma dot f equals f, well, yeah, for all functional germs. And maybe I'll sort of emphasize that they're functional germs. Okay, so yeah, so I'm modding out by the set of paths which act trivially on every functional germ. So now I want to note some stuff. So we know that this path, the path where we take a path in the upper left-hand corner and leave the bottom right-hand corner alone, we've got a path from x to x. This is supposed to be equivalent to, it's homotopic to, this other path where we just don't move in the first slot, but we do move in the second slot. So if I act on a germ by both of these things, so if I take gamma tau dot f, well, really, I take gamma dot f, tau dot f, that's supposed to be the same as if I take tau dot f, gamma dot f. But the point is that t is trivial, so this says that gamma dot f is really the same as f gamma dot f. So the point is that if I analytically continue the function f along this path, then what's going to happen here is that we get that gamma dot f equals f. And this gives us, this tells us that actually for an arbitrary path that this held. So what does that say? That says, therefore, basically everything inside of this thing that we modded out by, well, the stuff that we modded out by was everything, which then says that this pi functional of E is trivial. And so then what does that say? So the theorem here is free universal monodromy. And then that says that this pi functional of E is trivial, which then says that, i.e., the Monodrome theorem for sort of, well, so I'll say it in words. But so the point is that this says that this essentially this says that the Monodrome theorem holds for arbitrary functions which analytically continue along every path inside of matrices with spectrum inside some set. It's sort of more interesting than that whenever we go to several variables, because whenever we go to several non-commuting variables, we can define analogous objects in fairly natural ways. And the point is that this says that on arbitrary connected free non-commutative sets, the Monodrome theorem holds. And essentially, it's a very similar logic to this. You can basically do some sort of specific homotopy that just witnesses this. And this explains a lot of behavior that has been witnessed in the non-commutative case, like the existence of antiderivatives for arbitrary functions, this non-commutative Jacobian conjecture being true, and non-commutative harmonic functions having harmonic conjugates always, sort of the things where you expect there to be obstructions classically, there just aren't in this case. And it's because of the weird geometry of sets of matrices, which is actually not so dissimilar from the case for, I guess, classically for Lie groups, which always have abelian fundamental groups. So now I want to talk about the tracial fundamental group, because in some sense, because we know this free universal monodromy theorem, this pi functional of E is, the functional fundamental group is somehow, you know, trivial. So let's see if we can get anything out of these tracial functions. In fact, we can. So the important lemma here is that if you take the derivative of f in the tracial functional calculus at a specific matrix X in a matricial direction H, that happens to be equal to, I guess, the normalized trace of the derivative of f in the functional calculus, well, the derivative of f evaluated in the functional calculus at X times the direction H that you were going to evaluate in. So you take the derivative of f, just normally take the derivative, and then evaluate that in the functional calculus, and then you hit that with H inside of a trace. So a corollary here. So the point is here that whenever I take the derivative of a tracial function inside of a trace, and because we have enough sufficiently many directions, the point is that I get a functional calculus function involved in the derivatives, which then says that basically that, well, the following. So if I have gamma dot f in the tracial functional calculus minus f evaluated in the tracial functional calculus has to be constant. Because we know monodromy holds for functions that are evaluated in the classical functional calculus, and we know the derivative has this form, and the point is that because we can evaluate on sufficiently many h's, that means that we can sort of uniquely determine what this function was. Okay. So that's excellent, because then another corollary is if we let this a phi, which is depends upon f evaluated in the tracial functional calculus of just being evaluated at a point gamma to be just this gamma dot f trace minus f, this is a homomorphism into C. So what's important about that is that, so basically the point is that whenever I take eta dot gamma dot f trace minus f trace, point is that we know that this is the same as gamma dot f trace minus f trace. So then, because we know this, we can just sort of we could do the calculation of taking, so the point is that if I have a path eta and a path gamma, the point is that because this is constant, any path that acts on this is going to be trivial. And so then what's going to happen if I take eta dot gamma dot f trace minus f trace, well, then I could add this part in, and then I would get out something that's going to say that this is the same as if I'd taken them in. Well, so I can essentially say that this is the same as taking this plus this thing, this eta. So essentially, whenever you want to analyze this, you can use this to sort of show that this is actually a homomorphism. Okay. So the other thing to note here is because of the way that we define these fundamental groups, basically by modding out by, again, if we want to do this with traces, we're going to do this tracial fundamental group. We just do the same thing, but with tracial. And then here we'd have f trace. Then, okay, then we would get a pi tracial out here. So then what's the point here? The point here is that the collection of PF traces actually determine this pi trace. So the point is that an element is going to be the identity inside of this tracial fundamental group if and only if it's trivial for all, if it's 0 for all of these. Okay, so then what's the point here? Remember, so where, again, this pi trace E is just equal to the full fundamental group modded out by those gamma which act trivially. On tracial germs. Okay, so then the theorem here, because we have all of these homomorphisms into C, and we knew that, into C, I guess C with plus. The point is that because we know that, then what we can determine from this information is that this pi trace E is really isomorphic to some number of copies of Q. Now, I don't have any bound on how big that I is. It sort of might depend upon the number of holes, that kind of stuff. But this I is the cardinality of this index set I is going to be some unique number. Okay, so that's sort of nice because, okay, so we know that it's, because basically the thing that we know is we know that this pi full was a divisible abelian group. Whenever we take a quotient of that and we know that it's determined by homomorphisms into C, then we're going to get that those, via some sort of structure theorems, that this has to be some number of copies of Q. Okay, so that's sort of nice. And so the analytic continuation of these tracial functions isn't quite as good as analytic continuation in the actual functional calculus, but it's not that bad in the sense that it sort of is governed by the behavior of Q. And well, it's governed by this fairly simple abelian group. And I should also mention that you could develop, because we have this theory of this fundamental group, we could also develop a corresponding theory of the cohomology, which is also in the paper that describes these results. So we need to do a couple of examples, of course. Now, so if I have E being C set minus the point 0, well, what does that look like? It looks like C, but without one single point. Then if I take the classical fundamental group of that E, that's just going to be the integers. or well, isomorphic to the integers. And then if I take this pi full to be, that's going to be the same as pi tracial of e, which turns out to be q. And the way that the way that sort of, we shouldn't be too surprised about this because, okay, so what are the set of matrices with this as with C set minus 0 as their spectrum? Well, that's just GLN. We know that GLN for any n actually has fundamental group isomorphic to Z. And because of the way we define this full fundamental group to have this direct sum property, we just have to sort of take the division closure of that. And so we're going to get Q. Then it gets a little bit more interesting whenever we have domains that are a little bit more complicated, but not that much more interesting. And so then the key here is now if we take E to be, yeah, just C set minus point Z1 or well, Z2, then if I take pi 1 sub E, that's supposed to be a free group on 2 generators. So if I take classical fundamental group, that's a free group on 2 generators. But if I take the the full fundamental group, that's actually still isomorphic to the tracial fundamental group, which then is isomorphic to Q squared. So it's sort of like an Abelianization and division closure of this F2. These two examples are fairly simple because of the fact that we can do, there's certain techniques that sort of one can do to sort of use homology to calculate these by looking at the homology of each of the levels of this non-commutative set, if this set is sufficiently nice. And so I'll close with a couple of problems. In the theory. So here's a conjecture, which we don't know the answer to, but seems likely to be true due to some results of like Procesi. So if that pi full should be isomorphic to pi trace, including in sort of multivariable cases, which are sort of natural extensions of these definitions. I encourage you to at least skim the paper on archive. And so one conjecture is that these two things should be isomorphic. The other thing that I wanted to mention is a question is how to compute the well, just pi full slash pi tracial for domains of rational functions, of free rational functions. So one question, so there are two basic questions that I think would really help us understand a little bit better what's going on in this sort of non-commutative geometry and topology setup, which would be to determine if this pi full is really the same object as this tracial fundamental group, because the tracial fundamental group is this nice structure theorem. We know that pi full is some sort of Abelian divisible group, but we don't know that much more about it. And it would be nice if they just happen to be exactly the same. Because I would say that sort of tracial functions, which have been developed, by a variety of groups of authors recently, sort of capture the theory of this geometry and topology domains. And then the second thing that would be useful to know is how to compute these what is it called, fundamental groups, in the case where we have a fairly simple domain, which are, say, like the domains of free non-commutative rational functions, which just seems like, so that seems like a fairly tractable example of something that we might want to study. So I'd like to thank you a lot for listening, and I'd like to thank Fields for hosting this event and inviting me to give it, and everyone for inviting me to give a talk. So thanks.
Thank you. Questions, comments? So as usual, if you have a question, then just go ahead and all right. If there aren't any questions, then let's thank our speaker again. And we'll see you all tomorrow.
Thanks so much.
Mhm.